Hey. Hi everyone. Happy Friday. Let's go ahead and get started. So today, release bean. Today, we're going to talk about some important properties of integers. And the GCD. So these may be things that some of you have seen before, but since we're going to use them a lot over the course of the semester, I just want to set up some common language and results for us to use. So let's start off with just the definition of the integers. So we let, and I'll denote this with the so-called Blackboard bold Z. So this will be the set of all integers, positive and negative. So this is called the integers, and an element of this set is called an integer. And we'll also use this pretty frequently. So z subscript greater than or equal to 0. So this will be the set of just integers starting from 0. So this is the non-negative integers. And let's also do the positive integers. So we'll have z strictly greater than 0. So this is 1, 2, 3, and so on. So this is the positive integers. Okay, and this set of positive integers satisfies a very silly looking but very important property called the well-ordering principle. So and this is one of those weird things that I'm going to write down the statement and it's going to look totally obvious and you're going to wonder why I even bothered writing this on the board, but it turns out to be pretty powerful and comes up in a lot of different contexts. So this says that every non-empty set of positive integers contains a smallest element. Okay, so if I take any subset of the positive integers, then that subset has a least element. And we're going to take this as an axiom for now. But maybe to convince you that this isn't a completely silly idea, can anyone give examples of sets that do not satisfy this? I guess examples of sets of numbers that do not satisfy this. Yeah. Yeah, so The integers, for example, this does not satisfy it. And yeah, as an example, you can just take the integers. There is not a least element, right? Good. Other examples? Yeah. Yeah, okay, yeah. So the negative integers would also satisfy that. So I guess just going along with analogy of our notation, maybe you can just predict what this set is. So this also does not have a least element. Any others? Yeah. Yeah, so the complex numbers, this is an interesting example. So the complex numbers, you don't even have an idea of what it means for one number to be less than another. So in the complex numbers, we cannot compare numbers. So for example, like, is I less than 1 or is it greater than 1? I don't know what this means. And then another example that you could think of is the real numbers, and maybe even we'll take just the non-negative real numbers. So in here you can find, right, like open intervals is a subset of the real numbers that doesn't have a least element. So this is like another example. Okay, so maybe this this idea of the well-ordering principle isn't a completely silly thing, and we'll see an example today of how this is used, but we'll also see on Monday that this is like the reason why induction works. So on Monday we'll be talking about mathematical induction, and we'll prove a statement that's called the first principle of mathematical induction. And that statement tells you how to do proof by induction, and we'll do some examples. But that is completely reliant on the well-ordering principle. Okay, so let's talk about division. So just for starters, we're going to talk about what are divisors and what are prime numbers. So we'll have a definition. So we'll say a non-zero integer t is a divisor of an integer s if there exists an integer u such that s is equal to t times u. Okay, so in that case, you would also say like t divides s, and also u divides s. Okay, so the notation for this, we write t and then you put like a line, so t divides s is how you pronounce this. And then to say that a number does not divide another number, you put like a little slash through it. So this would be t does not divide s. Okay, and then a prime is just a positive integer greater than 1 whose only positive divisors are 1 and itself. Okay, any questions about divisors or primes, anything like this? Yeah.
Can't primes also be negative?
No. Like, I don't think you would say -3 is a prime number. At least for the purposes of this class, we'll always take them to be positive. Yeah. Anything else? Okay, so we're going to use the following theorem. So let's let A and B be integers with B greater than 0. Okay, so then there exist unique integers Q, which I think of as the quotient, and R, which I think of as the remainder, with the property that A is equal to BQ plus R, and R is constrained to be between 0 and B. Okay, so I'm not going to prove this theorem for the sake of time, but you can find a proof of it in the textbook. But maybe just looking at the statement, you can be convinced of this by recalling like the long division algorithm that you may have learned in grade school. So, you know, if you wanted to divide the number A by B, you would just repeatedly subtract off copies of B some number of times. That would be Q times, and then you're left with some remainder R. Okay, so this is a theorem about division, and this also looks pretty innocent, but we will, this will come in very handy. So, are there questions about this? Okay, so now I'm going to introduce the greatest common divisor, and then we'll spend almost the entire rest of the time proving a theorem about the greatest common divisor. And the name of this theorem is GCD is a linear combination, which I think is like an easy way to remember it. So let's introduce the GCD, and then we'll talk about the theorem. So we'll have a definition. So the greatest common divisor of two non-zero integers A and B is the largest of all divisors. Let's say this. So, of all integers which are divisors of both A and B. And this is denoted by GCD of A and B. And in some contexts, yeah. Does A what? Does A have to be greater than B? So Q could be 0, right? So let's do like a little example. So let's say, and also like A could be negative is the other thing. But let's say like A is 3 and B is 5. Then I would write this as A is equal to B times 0 plus 3. So yeah, so the remainder would just be all of A. Yeah, good. Yeah, I think it's good to, like whenever I write down a statement like this, to kind of like probe each of the assumptions, like why did we allow this number to fall in this range, or why did we ask this not to be 0, just to see like why the statement is the way it is and how it can break if you leave out assumptions. So this was like a good check. Okay, so the greatest common divisor. So in other, I'm just going to alert you of this because this, I don't think in our textbook it will appear, but in some contexts you will see this. So in situations like when you're studying number theory or something like that, and the GCD is really coming up like all the time, people will just write A comma B for the GCD. So like the first time I encountered this, I was like very, very confused. And I was like, the ordered tuple A comma B is not a number. But like, this is just like when people are using GCD a lot, they will just like drop the GCD and just write A comma B. I'm not going to do that, but just like be aware that if you're reading other sources and stuff, you may encounter this notation. Okay, so let's just quickly do some examples. So I'll give you like a minute to think through these. It's like, you know, this isn't too deep, but just so we have a grasp on this. Ah. Okay, so let's compute each of these. I'll give you like a minute. Okay, so you can just shout these out. What is the GCD of 12 and 16? Yeah, 4. What is GCD of 24, 9? And what about 12 and 35? Yeah, okay, so this is like a special situation. So whenever the GCD of two numbers, A and B, is equal to 1, you say that A and B are relatively prime. Okay, good. So let's state the theorem with the catchy name. So this theorem is called GCD is a linear combination. And you'll see why in just a second. So this is what it says, for any non-zero integers A and B, there exist integers s and t such that we can write GCD of a comma b as as plus bt. And actually, I'm going to scoot this down. Are there any questions about the statement? Any reactions to the statement? I always every time I see this, I'm just like, that is so weird. I feel like this is a very weird statement. Okay, so let's take a minute and for these examples, figure out how to write the GCD as a linear combination of those two numbers. So I'll give you a minute and then we can, we'll just talk about them. Okay, so how do we write the GCD as a linear combination in each of these cases? So how do we write 4 in terms of 12 and 16? Yeah. Yeah, so 12 times -1 plus 16 times 1. Okay, and what about for this one? How to get 3? Yeah. Yeah, so yeah, so yeah, this plus, is that what you're saying? Does that check out? Yes, okay, and then what about this last one? Okay, good. So here, these are just some examples of how to write GCD as a linear combination. So now let's prove the theorem. Whoop. So let's prove this. And the proof is a little bit tricky, I think. So let me just give an overview of how this is going to proceed. So the steps are going to be, first, we're going to write a subset. So we're going to write a set of integers containing all linear combinations and then we're going to use the well ordering principle to take the least element. And then we'll prove that this least element is in fact the GCD of these two numbers. Does the overall plan make sense? Yeah.
So, would we have to restrict SMT to be positive?
Yeah. Okay, so what we're going to have to do is restrict that the linear combination itself is positive. Because, so just going back to here, we had examples where one of S or T was negative, but we still got a positive answer. But yeah, so we are going to have to, restrict this set. Other questions about the plan? Okay, so let's write down this set. So we'll consider the set S, which is the set of all possible linear combinations. Let's just do it in terms of S and T. No, I'll do it. Okay, I'm going to do it this way. So AM plus BN, such that M and N are integers, and this whole quantity AM plus BN is positive. Okay, so now what I want to do is apply the well-ordering principle to this. So apply the well-ordering principle. But what do I have to do in order to apply the well-ordering principle? So what kinds of sets does the well-ordering principle apply to? Yeah. Yeah, so it has to be, so S has to be, S must consist of positive integers. Is this true? Yeah, because A, B, M, and N are integers, so this quantity will also be an integer, and then we also just asked that this was positive. So S does consist of positive integers. What is the other thing that S has to satisfy in order for us to apply the well-ordering principle? Yeah.
It has to be non-empty.
Yeah, so why is S non-empty? Yeah.
But why is that not already satisfied by S consisting of positive integers? If S consists of positive integers, then it's not empty, right?
So, okay, what if I computed all of these sums and it turned out that they were all negative? Is that possible, though? Why? Yeah.
What you could do is for because you can just come up with some linear combination that isn't zero. Basically take one of S, one of A or B. If it's positive, just have it be that. If it's negative, have it minus one.
So let's say we compute, for example, just A plus B. So if this was positive, then we're good. So if positive, then good. And if it's negative, then minus A minus B is in S. And if A plus B is equal to 0, then we can just take a different value. So we'll just do the same logic for A plus 2B or something. So yeah, you can just take really any non-zero linear combination, and if it's negative, then you could just multiply the entire thing by -1, and you'll get something that's in S. Okay, do we believe that S is non-empty? Okay, so we're good on this. Okay, so now we can apply the well-ordering principle. So by the well-ordering principle, S has a least element. And let's say that this is called D, and that D is written as AS plus BT. Okay, so now my claim is that this number D is equal to the GCD of A and B. So what do I need to prove in order to prove that D is the GCD of A and B? Yeah. Yeah, so we need to prove that D divides both of these. So we need to prove that D divides A and D divides B. And also that D is the largest among these. Okay, so let's start off by proving that D divides A. And I'm going to give you time to think about this on your own, maybe like 4 minutes. And my hint is that you'll have to use the division theorem that we saw earlier. So the hint is to write A as dq plus r. Okay, so I'll give you like a few minutes to think about how to prove that D divides A, and then we'll talk about it. And you can discuss with your neighbors as well. Okay, so let's discuss this. So if we write A as dq plus r, where we're asking that r is greater than or equal to 0 but less than d, then what can happen? So either r is 0, in which case we're done, because that would mean that d divides a, right? And if r is greater than 0, what I'm going to do is try and show that r is an element of S. And this will contradict the fact that d was the smallest element of S. So this contradicts d being the smallest. And so that would mean that this case can't happen. So let's see how r is an element of S. Okay, so from this equation, we know that r is equal to a minus dq. And we also know that d is equal to as plus bt. So let's substitute that in. So we get a is equal, so r is equal to a minus asq minus btq. And then now we can see that this is a linear combination of a's and b's, right? So this is a times 1 minus sq plus b times negative tq. Hopefully I did that without any errors. Okay, does it look good? So this is an element of S. So that concludes this part of the proof, and so we have that D divides A. Are there questions? Yeah, you look confused. Are you good? Yeah, question?
You have to prove that expression is greater than 0 for every S.
Oh. Yes. Okay, so the question was, so of course, in order for this to be in S, this needs to be greater than 0. Does anyone see why? Yeah. Oh yeah, our assumption is that r is greater than 0. Yes. Yeah, so r already was, right, so r is like the output of, it's the remainder of the division algorithm, so it automatically has to be greater than 0. Okay, so yes. Good, other questions? Okay, so then, right, so we proved that D divides A, and then D divides B. So we could just repeat this argument. In the exact same way, and we would also find that D divides B. So are we happy with that? Yes, okay. Okay, so now all that we're left to do is show, so we did this part and this part. We have to show that D is the largest among these possible values. D is the largest common divisor. Okay, so what is a proof strategy that we can use to approach this? Yeah. Yeah.
What makes R smaller than D? Like you said, if that would be a contradiction, because D should be small. What says that?
Yeah, so R is smaller than D because it's like the remainder from the division algorithm. So yeah, it's like constrained to be between 0 and D. Yeah. Any other things that are coming up as the argument is like sitting with you? Okay, so what is the strategy that we're going to do to prove that D is the largest among all possible common divisors? Yeah, do you have a suggestion?
Could you assume that you have a larger divisor than try to prove that multiplication factor?
Yeah, so I'm going to do something very similar to that. So we'll assume that we have some D prime, which is also a common divisor. And then we'll prove that D prime is smaller than D. Okay, so we'll just like assume we have some other one, and then from that prove that that one actually has to be less than D. Okay, so we're running a little tight on time, so I am just going to prove this without giving you time to think about it. So since D prime is a divisor of A and B, there exist K and H, so we can write A is equal to D prime H and B is equal to D prime K. Okay, so now I'm going to do a little rewrite of D in a tricky way. So we'll have that then, so D by definition was A times S plus B times T. And now we know that A and B each can be rewritten in terms of D prime. So we'll have that this is equal to D prime HS plus D prime KT. And this means, so I'll just rewrite this again. So then this means that D can be written as D prime times HS plus KT. Okay, so that means that D prime is a divisor of D. And so D is the greatest common divisor. Okay, how do we feel about this? Are you happy with this argument? Are there questions? Okay, so let me just finish with a teaser for next time. So there's a theorem called the fundamental theorem of arithmetic. which you've probably used actually in your life many times. So this says that every integer greater than 1 is a prime or a product of primes. So that's the first part, and then the second part is that this product is unique up to like possibly reordering the primes, but the set of primes and the multiplicities of them is unique. Okay, so we will on Monday talk about induction and prove the first part of this theorem. So that is what is coming up. And I'll see you all on Monday, and have a good weekend. Hi, did you all have a question?
Maddie, do you know anything about 1040?
Well,
1040.
what is it for me?
Richard Schwartz, fundamental quantum mechanics.
My, yes, about that course is that we'll just teach whatever they want.
That is
That's
exactly.
exactly what it is.
I mean, that's like what my kind of graph theory is. It's like,
Yeah, that's kind of what they
say
say.
whatever.
Yeah, what point is there still working?
Yeah.
Wait.
No, there's no like oversight really. Like no one has spoken to me about like what are you teaching them this semester?
Right.
Yeah.
So like last
So
semester,
you teach whatever you want.
last semester was my first semester teaching at Brown, and so Melody Chan gave me like her Canvas site for her 540 class, so I had access to like her notes and her problem sets and all that. But like
That's why some of the questions you were like, ah, I don't know how to do that. Let's do that one.
yeah, no one's like checking like did Maddie teach them about
They just
in the
put
master
full
class?
trust in you.
Yeah. You know, it's funny too because it's like a required class, right? For the year, so
That's kind of fun.
yeah.
It's a required class for a lot of, like, a lot of,
Yeah.
basically every STEM degree.
Yeah, nobody's having after like make sure you cover these topics. They're just like, you teach this class.
That's what I was like. Schwartz teaches